Hello everyone, I am Kavish Piltharia and I am here to discuss Data Science Internal 1 examination paper and its solution. Now let's start with section A, data cleaning. Here we have some fill in the blank questions. I will start by explaining them one by one. In Bayes' theorem, P of A by B equals. Now, uh, here it is about conditional probability actually. So, as you can see in the diagram, conditional probability. Bayes' theorem expresses how conditional probabilities are related, enabling calculation of P of A by B given P of A by B, P of A, and P of B, thus rewriting the understanding of probability. Practical applications. This theorem is pivotal in various fields, including machine learning and statistics, where it aids in making informed decisions based on prior knowledge and evidence. Now, let's move on to the next fill in the blank. It is about 68, 95, 99.7 rule, describes the probability mass of dash distribution. Uh, the 68, 95, 99.7 rule indicates that approximately 68% of data falls within one standard deviation, 95 within 2, 99.7 within 3 for a normal distribution. Uh, Now, moving on to the next fill in the blank, it is uh, the metric that measures uncertainty gained when replacing distribution A with B is called. It is called Kullback-Leibler divergence. Kullback-Leibler divergence measures the uncertainty gained when one probability distribution is replaced by another, quantifying how much information is lost in the process. Application is including machine learning to compare models and optimize performance by understanding distribution differences in data representation. Now the next fill in the blank, uh, ridge regression uses L dash penalty while lasso uses an L dash penalty. We can see that ridge regression employs an L2 penalty, which minimizes the sum of the squares of the coefficients, and lasso regression utilizes an L1 penalty, which encourages sparsity in the model by minimizing the absolute sum of coefficients. Now, moving on to the next fill in blank. Model that performs well on training data but fails on unseen data from. It is overfitting. Overfitting occurs when a model performs exceptionally well on training data but fails to generalize to unseen data, causing poor performance and new real world inputs. Now, moving on to sixth fill in the blank. In logistic regression, coefficients are estimated using the dash likelihood function. It is maximum likelihood function. Logistic regression, coefficients are estimated using the maximum likelihood function, which selects parameters to maximize the probability of observed labels fitting the model accurately. Now the next one, the hyperplane in SVM that maximizes distance between classes is called the dash margin hyperplane. It is called maximum margin hyperplane, which is a decision boundary in SVM that does the following function. Moving on to the next one. In clustering, K means minimizes the within clustered sum of. It minimizes the clustered sum of quad Euclidean distances, WS double S. ensuring data points are as close as possible to their respective cluster centroids. Now, the next one in PCA, the principal component captures the maximum possible data. Uh, it is about variance. In PCA, the first principal component captures the maximum possible variance of the data, indicating its effectiveness in summarizing the information contained within the dataset. Now, the next one, CNNs are particularly effective for dash data, while RNNs are suited for dash data. CNN is convolutional neural networks. They are highly effective for processing image and spatial data, as they capture local patterns through convolutional layers, enabling efficient feature extraction. Recurrent neural networks excel at handling sequential or time series data as they maintain memory of previous inputs, allowing them to model dependencies across time effectively. Now, the next one, in TensorFlow, the structure representing operations and dependencies is called a computational graph, which represents a network of operations and dependencies. Now, the next one, Hadoop's fault-tolerant distributed storage system is called. Uh, uh, Let us see what is written in the PPT. Uh, HDFS is designed for high availability, uh, ensuring data reliability through replication across multiple nodes, making it resilient to hardware failures and enhancing data accessibility. So it is some kind of a fault tolerant design actually, and distributed architecture. Now the next one, a SQL query combining rows from multiple tables based on related columns uses the dash clause. It uses the clause, as its justification is clear that it is essential for merging rows from multiple tables based on related columns, enabling complex queries across diverse datasets efficiently. Now, the next one, the Python collection that ensures only unique elements is called a. It is called a set. A set is a built-in data structure in Python that stores unordered collection of unique elements, providing efficient membership testing and eliminating duplicates automatically. Now, the next one, or should I say the last one, bootstrapping is a resampling method that samples dash replacement. Bootstrapping is a powerful statistical technique actually for estimating the distribution of a sample by repeatedly drawing samples with replacement from the original data set. So it's about the resampling method. Now moving on to the second section, which is machine learning concepts. Now let me tell you about how one matches to another. As you can see in the first column, the first one, Manhattan distance, matches to sum of absolute differences. It is because Manhattan distance calculates distances by taking the absolute differences of coordinates and adding them. It's called Manhattan because it behaves like navigating a city grid, moving only horizontally and vertically. Now, the second one, Euclidean distance, connects to straight line distance. Euclidean distance is the standard straight line, or as the crow flies, distance between 2 points. It is derived from the Pythagoras theorem and corresponds to the L2 norm. Now, the third one, Pearson coefficient, COV of x comma y upon sigma x star sigma y. Justification is clear. The Pearson correlation measures linear dependence between two variables. It is defined using covariance, scaled by the product of their standard deviations. The color ranges from -1 to +1, showing the strength and direction of a linear relationship. Now, the next one, Pearson coefficient, is related to correlation based on ranks. Pearson correlation is a rank-based non-parametric correlation. As you can see, it matches the right column. Now, the next one, L1 regularization, connects to shrinks some coefficients to zero. L1 regularization used in Lasso applies a penalty proportional to the absolute value of coefficients. All right. Now let's move to the sixth question. L2 regularization shrinks all coefficients proportionally. L2 regularization used in Ridge, as I explained earlier in the fill in the blanks, penalizes the square of coefficient values. This penalty does not zero out coefficients but smoothly reduces all of them. The next one, bagging, which connects to bootstrapped aggregation of trees. The justification is clear. Bagging stands for bootstrap aggregating. It trains multiple models on different bootstrapped subsets, sampling with replacement and averages their result. Examples include random forests. The eighth one, boosting, sequentially focuses on misclassified samples. The justification is boosting builds models sequentially, where each new model focuses more on the errors, misclassified samples of the previous model. The idea is to convert weak learners into a strong ensemble. On the next one, ridge regression connects to uses penalty lambda summation of beta square. The justification is ridge applies L2 regularization, adding lambda times the sum of square of coefficients to the loss function. This discourages excessively uh, large weights and helps prevent overfitting. It is especially effective when uh, predictors are correlated. The last match the column, lasso regression, which connects to uses penalty lambda summation of modulus of beta. Lasso applies L1 regularization, adding lambda times the sum of absolute values of coefficients. This penalty creates a sparsity in the model by setting some coefficients to zero, acting as implicit feature selection. It is useful when only a subset of features is truly important. Now, this ends section B of this internal. We would further do other sections, which are section C and D, uh, uh, in the next video actually. So thank you so much for your patience and watching this video. Thank you.